Have you ever wondered if we are alone? If, somewhere in the vastness of the cosmos, there might be another sky with oceans beneath it, another sun warming a world where something, anything, stirs, breathes, and looks up? It's one of the oldest questions humanity has ever asked. Not because we expect an answer, but because the question itself reveals who we are. Creatures aware enough to imagine company in the dark. When scientists speak of life beyond Earth, we often sound clinical, discussing molecules, temperatures, and chemical reactions. But at its core, this search is deeply philosophical. We are not merely asking whether bacteria swim beneath alien ice. We are asking whether existence itself repeats, whether consciousness is a local accident or a universal tendency. But before we can search for life elsewhere, we have to confront a deceptively simple question. What is life? You might think that's an easy one. You're alive. You breathe, think, eat, grow, and feel. Surely life means being able to do those things. Yet when biologists try to define it precisely, it slips through their fingers. A rock doesn't reproduce or metabolize. It's not alive. A tree does. It draws energy from sunlight, converts carbon dioxide into oxygen, grows, and even responds to damage. Viruses, on the other hand, exist in a strange twilight zone. They can't reproduce without hijacking the machinery of living cells, yet they evolve and adapt. Two hallmarks of life. So are viruses alive? Some say yes, some say no. The trouble is that life is not a single property, but a collection of processes. Self-maintenance, growth, reproduction, evolution, and response to environment. On Earth, all of these are carried out by complex systems of carbon-based chemistry. Carbon is the versatile architect of the biological world, forming the scaffolds of DNA, proteins, and sugars. And yet, even as we define life in chemical terms, we can't escape its poetry. To live is to resist entropy, to hold structure against the constant tendency of the universe toward chaos. Life is organized energy, fleetingly defying the silence of the void. On Earth, we have only one example of that defiance, our own. Every microbe, every fern, every whale, every human being is part of a single family tree that began perhaps 4 billion years ago, when chemistry became biology. That's all we've ever known. One planet, one origin, one example, which is both a miracle and a limitation. Because with only one example, how do we know whether life is rare or inevitable? If Earth were the only oasis in the desert of space, that would make us extraordinary, but also terribly alone. If, on the other hand, life sprouts wherever the right conditions exist, then the cosmos is teeming with cousins we've yet to meet. That is why we search, not merely to find aliens, but to understand ourselves. Each rover on Mars, each probe to the icy moons of Jupiter and Saturn, each telescope aimed at distant stars, is part of that great act of curiosity. The desire to know whether nature has repeated its grand experiment elsewhere. It is, in a sense, the ultimate form of introspection. To seek life beyond Earth is to look into a cosmic mirror and ask, how improbable am I, really? The search for life, known as astrobiology, lies at the intersection of many disciplines: astronomy, chemistry, geology, biology, and even philosophy. It is both humble and grand. Humble because we begin with dust and data. Grand because what we seek could rewrite the story of existence. The first step, however, is to understand why this world, our blue, improbable home, works so well. Because by studying Earth, we learn what life needs. And by knowing what life needs, we can begin to recognize it elsewhere. The Earth, in its quiet way, is our laboratory, our example, and our teacher. It floats in a narrow band around the sun, not too close, not too far. Astronomers call it the habitable zone, the region where temperatures allow liquid water to exist on the surface. That may sound trivial, but it's everything. Water is the great enabler of chemistry. It dissolves, transports, and reacts with a grace unmatched by any other liquid we know. Without it, the machinery of life cannot turn. Our planet also has the right atmosphere, thick enough to trap heat, thin enough to breathe. Oxygen feeds metabolism, nitrogen cushions chemical reactions. And beyond that invisible veil, a magnetic field shields us from solar radiation that would otherwise strip the planet bare. Even the tilt of Earth's axis, the pull of its moon, the balance of land and ocean, all play quiet roles in maintaining stability. The Earth is not merely lucky. It is exquisitely tuned by chance and time. This combination of water, energy, and chemistry is what scientists now use as a blueprint for finding other habitable worlds. Wherever these three meet, water, an energy source, and organic molecules, life, as we understand it, could emerge. Yet the more we look, the more we realize. The ingredients of life are not rare. They are written into the very fabric of the universe. Carbon, hydrogen, oxygen, nitrogen, the building blocks of biology, are also the most common elements in the cosmos. They are born in stars, forged in nuclear fire, and scattered across space when those stars die. Every living thing on Earth is, quite literally, made of stardust. So perhaps life is not a cosmic accident after all, but a natural consequence of chemistry given enough time and quiet. The question is no longer if the universe can make life, but where it has done so. To answer that, we start by following the chemical breadcrumbs scattered through space. Molecules drifting between the stars, frozen in comets, trapped in ancient rocks. These are the whispers of biology before biology existed. They tell us that the story of life might have begun long before Earth itself took shape. And that story, astonishingly, is still being written in the heavens tonight. If you could look at Earth from a few million miles away, through the cold lens of a distant telescope, you might notice something strange. Amidst the black silence of space, there is a world that shines blue. It glimmers not because of metals or glass, but because of oceans. Sunlight scattering through liquid water. That shimmer is a signature of life. And it's one of the first things astronomers now look for when they scan the skies. Our planet, this delicate sphere of blues and greens, is the only known example of a living world. To understand life beyond Earth, we begin here, because everything we know about biology, chemistry, and evolution originates from this tiny oasis in the cosmic desert. Earth sits in a rare sweet spot. It orbits the sun at just the right distance, about 150 million kilometers, where temperatures allow water to remain liquid. If Earth were a little closer, like Venus, the oceans would have boiled away into a suffocating atmosphere. A little farther, like Mars, and the oceans would have frozen solid beneath blankets of ice. Astronomers call this region the Goldilocks zone. Not too hot, not too cold. But distance alone isn't enough. The sun itself had to be the right kind of star. Too massive, and it would burn violently, exhausting its fuel in a few million years, far too short for complex life to evolve. Too small, and it would leave its planets tidally locked, one side scorched in perpetual day, the other frozen in endless night. The sun, by cosmic standards, is wonderfully ordinary, and that ordinariness is its greatest gift. Then there's the atmosphere, a fragile film only a few dozen kilometers thick, but utterly essential. It protects, moderates, nourishes. Oxygen fuels our cells, carbon dioxide warms the air, nitrogen provides stability. And floating within it are clouds, sculpted by temperature and wind, carrying water around the globe in an eternal cycle of evaporation and rain. Earth also possesses a magnetic field generated by molten iron swirling in its core. This invisible shield deflects the solar wind. Streams of charged particles from the sun that could strip away the atmosphere over time. Without that magnetic protection, Earth might look more like Mars, barren, red, and exposed. Even the moon plays a quiet but vital role. Its gravitational pull steadies the Earth's rotation, keeping our seasons consistent and preventing chaotic climate swings. It also tugs gently at our oceans, creating tides that may have stirred the chemistry of early life along ancient shorelines. Every aspect of Earth's design, its distance, its composition, its companion, its magnetic heart, seems almost too precise to be accidental. Of course, it isn't that the universe designed Earth for life. Rather, life emerged because Earth happened to have the right ingredients. Still, the coincidence is profound enough to make even the most rational scientists pause. But if Earth is our reference point, it is also our bias. We assume life elsewhere must resemble what we know, carbon-based, water-dependent, thriving under sunlight. That's a sensible starting place. But it may not be the whole story. Even here, on Earth, life has adapted to extremes that once seemed impossible. In the scalding vents of the deep ocean, bacteria thrive in water hot enough to melt lead. In Antarctic ice, microbes survive frozen for thousands of years, reawakening when conditions improve. In acidic lakes, in radioactive waste, in clouds high above the ground, wherever we look, life finds a foothold. We call these remarkable organisms extremophiles, lovers of extremes. They have taught us that life is far more flexible than we once imagined. It doesn't demand comfort. It simply demands opportunity. That realization changed everything. It told us that the conditions for life might exist in many more places than we thought. A planet doesn't need to be a perfect twin of Earth. It just needs energy, chemistry, and time. Water, in particular, became the compass of exploration. Not because water is magical, but because it does what few other substances can. It dissolves, mixes, and carries the ingredients of biology. Water allows molecules to meet, to react, to build complexity. In the beaker of the cosmos, it is the solvent of creation. When astronomers search for life, they follow the water. They look for traces of ice on rocky worlds, for vapor in alien atmospheres, for ancient riverbeds carved into dust. Because where water once flowed, life might once have been. And water, as it turns out, is everywhere. In comets, in moons, beneath the crust of Mars, even floating as vapor in the clouds of distant planets. The universe seems to be saturated with this stuff, frozen, liquid, or hidden. It's a humbling thought. We once imagined Earth as a special jewel, the only blue planet in a sea of emptiness. But with every discovery, that uniqueness erodes a little more. Maybe oceans are not so rare. Maybe biology is not an anomaly. but a pattern waiting to repeat. Still, when you step outside at night and look up, it's hard not to feel the weight of the void. The stars are silent, distant, ancient. We've sent probes, signals, and telescopes, and so far, nothing is answered. And yet, silence does not mean absence. It only means the conversation hasn't started, or that we have not yet learned the right language to listen. To find that language, we first follow chemistry, the story written not in words, but in atoms. Because before there was life, there were molecules. And those molecules, it turns out, are older than any planet. They drift in clouds between the stars, forming in the cold darkness of space, tiny seeds of potential that one day might awaken. When scientists talk about life, we often start not with organisms, but with chemistry. Because before there were cells, or DNA, or even oceans, there were atoms that learned to form bonds. Life, at its most basic level, is chemistry that learned to persist. And the chemistry of life, at least the kind we know, is built on 4 main ingredients: carbon, water, energy, and time. Let's begin with carbon. Carbon is, in many ways, the unsung hero of biology. It's a small atom, simple in structure with 4 electrons in its outer shell. That means it can form up to 4 bonds with other atoms, a perfect foundation for building complex molecules. Think of it as the Lego brick of the universe. It connects easily and stably, yet flexibly enough to create infinite combinations. A single carbon atom can link with others to form long chains, branching trees, or even ring-shaped molecules. From these, you can construct sugars, fats, amino acids, and nucleotides, the molecules that make up proteins and DNA. Without carbon's versatility, there would be no biochemistry. And carbon is not rare. It's one of the most common elements in the universe, forged in the hearts of stars and scattered into space when those stars explode. Every breath of air, every grain of soil, every living thing on Earth, all of it owes its structure to carbon created billions of years before the Earth even existed. Next comes water, the second key ingredient. Water is a peculiar liquid. Its molecule, H2O, is deceptively simple. 2 hydrogen atoms bound to 1 oxygen atom. But its properties are extraordinary. Water is polar, meaning one end of the molecule carries a slight negative charge, and the other a slight positive charge. That polarity allows water molecules to stick to each other, to dissolve countless substances, and to create an environment where chemical reactions can occur efficiently. In biology, water acts as both a solvent and a transport medium. It dissolves minerals, carries nutrients, stabilizes temperature, and even participates in chemical reactions itself. It's not an exaggeration to say that without liquid water, life as we know it simply couldn't exist. Then there's energy. Life needs energy to organize itself, to build, move, reproduce, and repair. On Earth, the ultimate source of that energy is the sun. Sunlight drives photosynthesis, the process by which plants and certain bacteria capture light and convert it into chemical energy. That energy then flows through ecosystems as animals eat plants, and other animals eat them in turn. But sunlight isn't the only option. Some organisms, especially those living in the deep ocean, draw their energy from chemical reactions instead. Around hydrothermal vents, bacteria use hydrogen sulfide, methane, or iron compounds as energy sources. These so-called chemotrophs live in total darkness. proving that life doesn't depend on sunlight, only on the flow of usable energy. This discovery was one of the most important in modern biology because it opened the door to a new way of thinking about life elsewhere. If organisms on Earth can thrive kilometers below the ocean's surface, feeding on minerals and heat from the planet's core, then maybe alien life doesn't need sunshine either. Maybe it just needs chemistry and warmth, even beneath the ice of a distant moon. The fourth ingredient, often overlooked, is time. Life doesn't appear instantly. The complex chemistry that leads to biology requires billions of years of subtle experimentation. On early Earth, simple molecules gradually formed more complex ones. Some began to self-replicate, using energy from sunlight or volcanic activity. Over millions of generations, these primitive chemical systems evolved into the first true cells. We call that transition abiogenesis, the process by which non-living matter becomes living. It's one of the hardest scientific puzzles we face. We don't yet know exactly how it happened, but we can see hints of it preserved in the chemistry of life today. The structure of RNA, for example, suggests it might once have served both as a carrier of information and as a catalyst for reactions, a sort of molecular missing link between pure chemistry and biology. When scientists search for life elsewhere, they are really searching for conditions that allow abiogenesis to occur again. That means they look for the three essential ingredients: carbon-based molecules, a source of energy, and liquid water. Interestingly, these same conditions appear to be quite common in the universe. Meteorites that have fallen to Earth contain amino acids, the basic components of proteins, formed naturally in space. Comets, which orbit the sun like icy time capsules, are rich in organic compounds. Even the thin clouds of dust between the stars contain molecules such as formaldehyde, methanol, and simple sugars. This tells us something extraordinary. The chemistry that gives rise to life doesn't require a planet at all. It can begin in the cold vacuum of space, long before any world is born. When you think about that, the origin of life stops being a miracle and starts looking like a natural part of cosmic evolution. The universe, through its laws of physics and chemistry, seems predisposed to build complexity. From atoms to stars to cells to minds. It's as though the raw ingredients of life are written into the fabric of existence itself. Still, chemistry is just the starting point. The question that truly fascinates scientists is where those ingredients might have come together, where conditions were calm enough, warm enough, and stable enough for life to take root. To answer that, we look not into theory, but into the evidence scattered across our solar system. Because if the building blocks of life are universal, the next question is, where have they already landed? And one of the first places we looked, and still look, is the small, cold, red world next door. When scientists first began to study the chemistry of space, they expected it to be simple, just hydrogen, helium, and a few trace gases drifting between the stars. But the more we looked, the more complex it became. The universe, it turns out, is not chemically barren. It's surprisingly rich. Using radio telescopes, astronomers can detect specific wavelengths of light emitted or absorbed by molecules. Each type of molecule leaves a kind of fingerprint, a spectral pattern that reveals its identity. In the 1970s, when these instruments became sensitive enough, scientists began to spot those fingerprints everywhere. Formaldehyde, methanol, ammonia, and even more complicated molecules, some containing 10, 20, or more atoms. Among them were organic compounds, the kind used in biological systems on Earth. This discovery was revolutionary. It meant that organic chemistry doesn't only happen inside living cells or on warm planets. It happens naturally in space, in the cold, dark clouds of gas and dust where stars are born. Inside these interstellar clouds, temperatures can drop to just a few dozen degrees above absolute zero. Yet, somehow, the dust grains floating there act as tiny chemical laboratories. Atoms of carbon, hydrogen, oxygen, and nitrogen stick to their surfaces, combine, and form new molecules. Over millions of years, these dust particles clump together into comets, asteroids, and planets, carrying with them the seeds of future life. When those comets or asteroids eventually collide with young planets, they deliver those molecules to the surface. That's not speculation. It's something we can measure. In 1969, a meteorite landed near the town of Murchison in Australia. When scientists analyzed it, they found more than 70 different amino acids, the very same kinds that make up proteins in living organisms. But here's the crucial part. Those amino acids weren't contamination from Earth. They had formed in space long before the meteorite ever fell. Other meteorites since then have shown the same pattern. Some even contain sugars and nucleobases, the molecular letters of DNA and RNA. This means that the raw ingredients for life are not unique to Earth. They're cosmic. They form naturally, in abundance, all over the galaxy. The European Space Agency's Rosetta mission gave us another clue. In 2014, its lander, Philae, touched down on a comet named 67P Churyumov-Gerasimenko. Instruments detected organic molecules in the comet's thin atmosphere, including formaldehyde and glycine, one of the simplest amino acids. Even in the deep cold, far from any sun, the chemistry of life was quietly taking place. NASA's Stardust mission found similar results when it collected dust particles from comet Wild 2 and returned them to Earth. And more recently, the James Webb Space Telescope, our most advanced eye in space, has detected carbon-based molecules in protoplanetary disks around young stars. These are the nurseries where new worlds are forming. In other words, the building blocks of life are already there when planets are born. That changes how we think about biology. Instead of imagining life as something rare that happens only under perfect circumstances, we now see it as part of a continuum, a natural outcome of cosmic chemistry. It's not that life appears against the odds. It might be that the odds favor it. Consider this. Every atom of carbon in your body was once inside a star. Every molecule of water you've ever touched was formed billions of years ago in the cold interstellar medium. Life didn't begin on Earth so much as it arrived here, carried on starlight and stone. There's even a theory for that idea, known as panspermia. It proposes that life, or at least its ingredients, can travel between planets on meteorites and comets. Some bacteria on Earth can survive radiation, vacuum, and extreme cold, meaning that if they were ejected into space by an impact, they might remain viable for millions of years. If panspermia is correct, life could spread naturally from world to world, given enough time. It's an intriguing thought, that biology might be a galactic phenomenon, not a planetary one. But even if life began independently on Earth, the chemistry that made it possible was universal. It tells us that the line between living and non-living is not a brick wall, but a gradient. Somewhere between chemistry and biology, the universe crosses a threshold and atoms start telling stories. Our next step is to look at worlds close enough to study directly. Places that show hints of those same conditions, where water once flowed and where chemistry still whispers of possibility. And the first stop on that journey is the planet that's been staring back at us for centuries, glowing faintly red in the night sky. If there's one planet that has captured the human imagination more than any other, it's Mars. For centuries, we've looked at that red dot in the sky and wondered what it might hide. Ancient astronomers thought it was a wandering star. Later, telescopes revealed a world with ice caps, seasons, and shifting patterns on its surface, enough to spark dreams of alien civilizations. By the late 19th century, some observers believed they could see canals on Mars, straight lines crisscrossing the planet's surface. They thought they were built by intelligent beings trying to irrigate a dying world. The idea turned out to be an optical illusion, but it planted a seed. Mars became a symbol of possibility, a world that could, maybe, be alive. Today we know far more. Mars is a cold, dry desert, smaller than Earth, with about 1/3 of its gravity and a thin atmosphere made mostly of carbon dioxide. The surface temperature can swing from a mild 20 degrees Celsius during the day to -100 at night. The air is too thin to breathe, and radiation from the sun bombards the surface unfiltered. On the face of it, it seems utterly hostile. And yet, Mars is not dead. It's just dormant. We now know that billions of years ago, Mars was a very different place. Orbital images show the remnants of ancient river valleys, deltas, and lake beds. Minerals found by landers like Opportunity and Curiosity indicate that those waters were once neutral, even drinkable. There were floods, erosion, and chemical reactions that could have supported life. In other words, Mars once had all three ingredients we associate with habitability: water, energy, and the right chemistry. The discovery of hydrated minerals, rocks that formed in the presence of liquid water, was one of the first major clues. Then came the detection of ice beneath the surface. In 2008, NASA's Phoenix lander dug into the Martian soil and uncovered bright patches that evaporated in the thin air. That was water ice, the real thing. We've since confirmed that frozen water exists at the poles and likely in underground reservoirs closer to the equator. Some radar data even suggest that beneath the Martian South Pole lies a buried lake of liquid water, kept from freezing by salts and pressure. Water, of course, doesn't guarantee life, but it does mean Mars once had the conditions that could support it. That's why modern missions focus on finding direct evidence of biology, either fossilized remains of ancient microbes or chemical traces of organic material. NASA's Curiosity rover, which has been exploring Gale Crater since 2012, found organic molecules in 3-billion-year-old rocks. These aren't proof of life, but they are the fingerprints of life's chemistry. Its successor, Perseverance, is taking the next step. It's collecting rock samples that will eventually be returned to Earth for analysis. A project involving both NASA and the European Space Agency. Those samples might, for the first time, tell us whether Mars ever hosted life. There's also the question of methane, a gas that on Earth is largely produced by living organisms. Methane has been detected in the Martian atmosphere in small, fluctuating amounts. That's puzzling, because methane breaks down quickly in sunlight. If it's still there, something must be replenishing it, either geology or biology. Some scientists suggest that chemical reactions between water and certain rocks underground could generate methane naturally. Others point out that on Earth, microbes known as methanogens do exactly that. So which is it? We don't yet know. But either explanation would be fascinating. One points to active geology, the other to possible biology. It's worth remembering that life, if it ever existed on Mars, would have been microbial. Simple, microscopic organisms adapted to a harsh environment. Even that would be monumental. To find a single fossilized bacterium on another planet would prove that life is not unique to Earth. It would change biology forever. And if life never existed there, that too is valuable knowledge. It would tell us that even with the right ingredients, life might still be rare. Either way, Mars will give us an answer. There's also the possibility that Mars is not lifeless now, but hiding its life underground. Beneath the surface, where radiation is weaker and temperatures are more stable, pockets of salty water might still exist. If microbes survived from ancient times, that's where they'd be, in dark, briny habitats, waiting out the cold ages. To test that idea, future missions will drill deeper, maybe a few meters below the surface, looking for organic molecules shielded from radiation. The upcoming ExoMars mission, developed by the European Space Agency, aims to do just that. The exploration of Mars has become a slow but steady detective story. Layer by layer, we're reconstructing the planet's past. And in that past, we see a reflection of our own. Both Earth and Mars began with oceans, volcanoes, and thick atmospheres. But while Earth remained stable enough for life to flourish, Mars lost its protection. Its magnetic field faded, its atmosphere thinned, and its water evaporated into space. You could think of Mars as a warning, a reminder that habitability is fragile, that even small changes can turn a living world into a frozen desert. And yet, it's also a symbol of hope. Because if life managed to begin there, even briefly, it means that life is not a miracle, it's a tendency. And if that tendency exists here and on Mars, then surely it exists elsewhere too. Maybe beneath the ice of a distant moon, or in the clouds of a faraway planet. And so, our search continues, outward, into the deeper reaches of the solar system, where even colder and stranger worlds may hold warm secrets beneath their frozen shells. When we think of places that could host life, we usually imagine planets, warm worlds bathed in sunlight. But some of the most promising environments for life in our solar system are not planets at all. They're moons, small, frozen worlds orbiting giant planets, hiding oceans beneath their icy surfaces. Two of them stand out: Europa, one of Jupiter's moons, and Enceladus, a moon of Saturn. At first glance, they look inhospitable. Both are bright, smooth, and covered entirely in ice. Temperatures on their surfaces hover around minus 160 degrees Celsius. No sunlight reaches the ocean below, and the airless vacuum above offers no protection from radiation. And yet, beneath that frozen crust, each of these moons hides something extraordinary: a global ocean of liquid water. Let's start with Europa. It's slightly smaller than Earth's moon, and from a distance, its surface looks like cracked glass. streaked with dark lines that stretch for thousands of kilometers. Those lines are fractures in the ice, created by the gravitational tug-of-war between Europa and Jupiter. As Europa orbits, Jupiter's immense gravity squeezes and flexes it. That constant tidal stress generates frictional heat within the Moon's interior, preventing the ocean beneath the ice from freezing solid. In effect, Jupiter's pull acts like a slow heartbeat, keeping Europa's ocean alive. Data from NASA's Galileo spacecraft, which orbited Jupiter in the 1990s, confirmed that this ocean exists. The spacecraft detected fluctuations in Europa's magnetic field consistent with a salty, conductive liquid beneath the surface, in other words, seawater. Estimates suggest that Europa's ocean may be 60 to 150 kilometers deep. To put that in perspective, Earth's deepest ocean trench, the Mariana Trench, is just 11 kilometers deep. Europa may hold more water than all of Earth's oceans combined. And where there's water, there's potential for life. The energy that drives Europa's tides could also drive hydrothermal activity. Heat and chemicals rising from the rocky sea floor, just like the vents on Earth's ocean floor. Around those vents, on our own planet, entire ecosystems thrive. Bacteria, worms, crustaceans, and other creatures living in total darkness, powered not by sunlight, but by chemistry. If such vents exist on Europa, they could provide the same kind of energy that supports life here. We don't know if anything lives there, but the conditions are tantalizing. NASA's upcoming Europa Clipper mission, scheduled to launch soon, will orbit Jupiter and make dozens of close flybys of Europa. Its instruments will map the surface, measure the thickness of the ice, and analyze the chemistry of the material ejected into space by the Moon's geysers. Yes, geysers. In 2012, the Hubble Space Telescope detected plumes of water vapor erupting from Europa's south pole, shooting hundreds of kilometers into space. Those plumes are windows into the ocean below, natural samples being delivered right into space, where a spacecraft could fly through them and test their composition. If those plumes contain salts, organic molecules, or traces of biological activity, we might finally have the first real evidence that life exists beyond Earth. And Europa is not alone. 1 billion kilometers farther from the Sun, orbiting Saturn, lies Enceladus, even smaller, only about 500 kilometers wide, yet remarkably active. In 2005, NASA's Cassini spacecraft made a discovery that astonished everyone. As it flew near Enceladus, it detected jets of water vapor, ice particles, and organic compounds spraying from cracks in the Moon's south pole. Features scientists now call tiger stripes. Cassini flew directly through those plumes and analyzed their composition. What it found was extraordinary. The vapor contained water, carbon dioxide, methane, ammonia, and complex organic molecules. Even more importantly, the presence of tiny silica particles suggested that the water had interacted with hot rock, evidence of hydrothermal vents at the bottom of Enceladus's ocean. That means Enceladus has everything life needs: liquid water, organic chemistry, and a source of energy. To put it simply, if microbes could exist anywhere beyond Earth, Enceladus would be one of the best candidates. The idea that life could thrive in darkness, beneath ice, far from any sun, has transformed how scientists think about habitability. It shows that warmth from a star isn't strictly necessary. The heat generated by tidal forces, the squeezing and stretching from a planet's gravity, can be enough to keep an ocean alive. It also means that moons around other planets, even outside our solar system, could host similar conditions. There may be countless ice worlds in the galaxy, each with hidden oceans under their crusts. The discovery of these ocean worlds has been one of the most exciting chapters in modern astronomy. It tells us that life might not need Earth-like continents and blue skies, only chemistry, heat, and persistence. When the Cassini mission ended in 2017, scientists deliberately sent the spacecraft crashing into Saturn to avoid contaminating Enceladus with Earth microbes. That decision reveals something profound. We now take the possibility of alien life seriously enough to protect it. In the coming decades, missions will return to these moons, equipped with more advanced instruments. Some will fly through the geysers again. Others might land and drill into the ice. If we ever find life beyond Earth, Europa or Enceladus might be where it happens. Tiny, frozen moons, orbiting far from the warmth of the sun, may hold the key to one of humanity's oldest questions. And just when we thought we understood what habitable meant, another world reminded us to think bigger still. That world is Titan, a place where rivers and lakes flow not with water, but with liquid methane. Among all the moons in our solar system, Titan stands apart as something truly unusual. It's the largest moon of Saturn, even bigger than the planet Mercury, and it's the only moon known to have a thick atmosphere. If you could stand on its surface, the sky would glow orange and hazy. You'd feel a light pressure, a bit stronger than Earth's, and the temperature would hover around minus 180 degrees Celsius. It's cold enough to freeze water harder than stone. But despite that alien chill, Titan feels strangely familiar. It has rivers, lakes, rain, and even weather, just not made of water. Instead, everything there flows with liquid methane and ethane. It's a world where the role of water is played by hydrocarbons, and the role of rock is played by ice. The European Space Agency's Huygens probe, which landed on Titan in 2005, gave us our first close look. As it descended through the thick orange clouds, its cameras revealed a landscape shaped by erosion and flow. Valleys, channels, and smooth pebbles scattered across a frozen plain. It was like seeing Earth's geology replayed in a mirror, but made from different chemistry. That moment was astonishing. For the first time, humanity had landed on a world beyond Mars and found another place with a hydrological cycle. On Earth, sunlight drives water to evaporate, condense, and fall again as rain. On Titan, the same process happens with methane. The atmosphere is dense enough to form clouds, and from time to time, methane rain falls gently onto the icy ground, filling dark lakes that glisten in radar images. It's a surreal version of home, familiar in shape, alien in substance. The question scientists immediately asked was, could something live there? Life as we know it depends on liquid water, but Titan challenges that assumption. Its lakes are far too cold for water-based chemistry to function. Yet methane and ethane are solvents too. They can dissolve certain organic molecules and enable reactions, albeit at much slower rates. If any world could host life that doesn't follow Earth's rules, Titan would be it. Researchers call this idea alternative biochemistry. Instead of carbon and water forming the foundation, life on Titan might use different chemistry altogether. Perhaps its cell membranes are made of methane-resistant materials, or its metabolic reactions are powered by other compounds, like hydrogen or acetylene. In 2015, a team at Cornell University modeled what such methane-based cells might look like. They called them azotosomes, membranes built not from phospholipids, like those in earthly cells, but from nitrogen-containing molecules that could remain stable in liquid methane. The simulation suggested that these structures could form spontaneously at Titan's temperatures. It was the first real evidence that life might not require water at all, only a solvent and the ability to organize. It's a radical idea, but one that reflects a growing trend in astrobiology. To stop assuming Earth's recipe is the only one that works, and Titan, more than any other world, invites that kind of imagination. NASA's Cassini spacecraft studied Titan for more than a decade. Using radar and infrared instruments to see through the haze, it mapped rivers and lakes concentrated near the poles. Some are hundreds of kilometers across. True seas of liquid hydrocarbons. The largest, called Kraken Mare, contains enough methane to fill the Great Lakes of North America several times over. Cassini also detected organic molecules in Titan's atmosphere. Complex chains of carbon, nitrogen, and hydrogen. Sunlight, weak as it is at Saturn's distance, still breaks apart methane molecules high above the surface, triggering chemical reactions that create smog-like layers of heavier compounds. These molecules eventually fall like snow, coating the ground in organic dust. In other words, Titan is constantly producing the raw materials of life. It's just doing so at a temperature where they remain frozen, waiting. Scientists sometimes describe Titan as a laboratory frozen in time. It may resemble what early Earth looked like before life began, rich in organic chemistry, but lacking liquid water. If Titan ever warms up, perhaps billions of years from now, those frozen materials could melt and react, potentially creating life as we know it. And there's another fascinating possibility. Titan's interior might contain a subsurface ocean of water and ammonia beneath its icy crust, much like Europa and Enceladus. That would mean Titan could host two very different kinds of environments. One of liquid methane at the surface, and another of liquid water below. That duality makes Titan a prime target for exploration. NASA is preparing a mission called Dragonfly, a robotic drone designed to fly through Titan's thick atmosphere. Scheduled to launch in the 2030s, Dragonfly will hop from one location to another, analyzing surface chemistry and searching for signs of prebiotic molecules. It will study dunes, lake beds, and the remnants of ancient impact craters, places where organic chemistry might be most active. Imagine that. A drone flying in alien skies, over seas of methane, scanning for molecules that might represent a completely different form of life. Whether Titan's chemistry ever crosses the threshold into biology remains to be seen. But even if it doesn't, it teaches us something profound. It reminds us that our definition of life may be far too narrow. The universe could be full of systems that behave like life, storing energy, adapting to their environment, evolving, yet built from substances we wouldn't recognize. For most of human history, we assumed that life required sunlight and warmth. Titan shows that it might instead thrive in cold and darkness, given the right chemistry. It's a humbling realization. Life, it seems, is not fragile. It's adaptable, creative, and opportunistic, willing to take whatever the universe offers. And as we expand our search beyond Titan, that flexibility becomes our new guiding principle. Because out there, orbiting stars far beyond the reach of our spacecraft, there are thousands of worlds. Planets that may look nothing like Earth, yet might be just as alive. For most of human history, we believed our solar system was unique. The stars we saw in the night sky were distant suns, yes, but we had no proof that any of them had planets of their own. It wasn't that people didn't imagine it. Philosophers as far back as the ancient Greeks speculated that countless worlds must exist. But imagination is one thing. Evidence is another. Then, in the early 1990s, everything changed. In 1992, two astronomers, Alexander Voltschan and Dale Frail, announced the discovery of planets orbiting a pulsar, a type of rapidly spinning dead star. It was a strange place to find planets, but it proved that other worlds existed. 3 years later, in 1995, a team led by Michel Mayor and Didier Queloz discovered 51 Pegasi b, the first planet found orbiting a sun-like star. It was a hot Jupiter, a massive gas giant orbiting extremely close to its star, completing one orbit every 4 Earth days. That discovery opened the floodgates. Since then, astronomers have confirmed more than 5,000 exoplanets, and the number grows every year. We now know that planets are not rare. They're common. On average, every star in the Milky Way probably has at least one planet, and many have entire systems like ours. The diversity of these worlds is astonishing. Some are gas giants larger than Jupiter. Others are small and rocky like Earth or Mars. There are planets that orbit 2 suns, like in Star Wars. There are worlds covered in oceans, worlds made mostly of ice, and even planets so close to their stars that their surfaces are molten lava. The more we look, the stranger the universe becomes. But amid all that variety, scientists focus on one special category: the habitable zone, the region around a star where temperatures are just right for liquid water to exist on a planet's surface. Not too hot, not too cold. What astronomers sometimes call the Goldilocks zone. Finding a planet in that zone doesn't guarantee it's habitable. It could have a poisonous atmosphere or no atmosphere at all. But it's a good starting point. To detect these distant worlds, astronomers rely on clever techniques. The most common is called the transit method. When a planet passes in front of its star from our point of view, it blocks a tiny fraction of the star's light, like a moth crossing a lamp. Sensitive telescopes can measure that dip in brightness and calculate the planet's size, orbit, and sometimes even its atmospheric composition. NASA's Kepler Space Telescope, launched in 2009, used this method to monitor over 150,000 stars. During its mission, Kepler discovered thousands of exoplanets and revealed that small, Earth-sized planets are remarkably common. Before Kepler, we didn't know whether our planet was rare. After Kepler, we learned it's probably typical. More recently, the James Webb Space Telescope, or JWST, has pushed the search even further. It can detect faint signals of gases in exoplanet atmospheres by analyzing the starlight that filters through them during a transit. Each gas absorbs specific wavelengths of light, leaving a spectral fingerprint. So far, JWST has detected molecules like carbon dioxide, methane, and water vapor in the atmospheres of several exoplanets. These are not yet signs of life, but they are signs of chemistry, the kind of chemistry that could lead to life. The most exciting targets are the so-called super-Earths and mini-Neptunes. Planets larger than Earth, but smaller than Neptune. Some of these worlds orbit small, cool stars called red dwarfs. Because those stars are dimmer than the sun, their habitable zones are closer in, making their planets easier to observe. One of the most promising systems is TRAPPIST-1, about 40 light-years away. It has 7 Earth-sized planets, 3 of which lie in the habitable zone. Imagine that. 7 rocky worlds, orbiting a single dim red star, each one potentially with its own atmosphere and oceans. We don't yet know if any are truly habitable, but if life exists anywhere beyond Earth, TRAPPIST-1 would be an excellent place to look. Another fascinating discovery came from a planet called K2-18b, located about 120 light-years away. Observations with JWST detected signs of carbon-bearing molecules, including methane and carbon dioxide, in its atmosphere. There's even tentative evidence of dimethyl sulfide, a compound produced by biological processes on Earth, though the finding remains uncertain. If confirmed, it would be the first hint, just a hint, of extraterrestrial life. It's important to remember that these detections are extremely difficult. The signals are faint, and even small errors can mimic biological signatures. But each observation refines our understanding of what's possible. We are now at the stage where science fiction is becoming data. The next generation of telescopes will go even further. Missions like LUVOIR and HAB-X, still in the planning stages, aim to directly image Earth-like planets and analyze their reflected light. That will allow scientists to search for so-called biosignatures, combinations of gases that could indicate life, such as oxygen and methane existing together. On Earth, that mix is sustained by living organisms. If we were to detect such a combination on another world, it would be one of the most profound discoveries in history. But even if we don't, the search itself teaches us something remarkable. Life-friendly conditions are not rare. The universe seems to be full of them. There may be billions of planets with oceans, clouds, and atmospheres just like ours. Somewhere among them, perhaps, there are eyes looking back, wondering the same thing we do. And yet, despite all our discoveries, we still face a great mystery. If there are so many potentially habitable worlds, why haven't we found life yet? Why haven't we heard from anyone? That question has a name, the Fermi paradox. And it forces us to confront not just the science of life beyond Earth, but also what it means for us to be alone. For most of human history, the search for life beyond Earth was purely philosophical. People could wonder, dream, or pray about it, but they had no means to test the question. That changed in the 20th century, when technology finally gave us the tools to turn imagination into investigation. Today, scientists search for life in 2 main ways. The first is astrobiology, studying the conditions that make life possible and looking for evidence of it, especially microbial life within our own solar system. The second is SETI, the search for extraterrestrial intelligence, listening for signals or patterns that might indicate advanced civilizations beyond our reach. Astrobiology starts close to home. We send robotic explorers to nearby planets and moons to ask a simple but profound question. Could life exist here, even in microscopic form? NASA's Perseverance rover, currently exploring the Jezero crater on Mars, carries instruments designed to analyze rock chemistry in exquisite detail. It can detect organic molecules, measure mineral composition, and even cache samples for future return missions. Each scoop of Martian soil is a small experiment, a test of whether the chemistry of life ever took hold there. Elsewhere, the Europa Clipper mission will soon head toward Jupiter to study the icy moon Europa and its hidden ocean. Its radar and spectrometers will look for signs of salts, organics, or thermal activity. All indicators that the ocean below might be chemically alive. Saturn's moon Enceladus has already given us its calling card. Those great geysers of water vapor and organic molecules spraying into space. A future spacecraft might one day fly through these plumes again, equipped with instruments sensitive enough to detect amino acids, lipids, or even the faint signatures of metabolism. If we find anything biological on one of these worlds, even a single microbe, the implications would be staggering. It would mean life arose twice, once on Earth and once somewhere else, suggesting that the universe might be teeming with it. But the search doesn't stop with biology. We also look for technology. SETI, the search for extraterrestrial intelligence, began in earnest in 1960, when astronomer Frank Drake pointed a radio telescope at two nearby stars and listened for artificial signals. He heard only silence, but his experiment became the foundation of a new scientific field. Radio waves are ideal for interstellar communication. They travel long distances. They're not easily absorbed by interstellar dust, and they're cheap to generate. If an intelligent civilization wanted to announce its presence, radio would be a sensible choice. Since Drake's pioneering effort, SETI researchers have scanned millions of frequencies across thousands of stars. Modern projects like the Allen Telescope Array and the Breakthrough Listen initiative use advanced computers to sift through vast amounts of data, searching for narrow-band signals that nature doesn't produce on its own. So far, we've found nothing conclusive, only a few brief, unexplained bursts of radio energy, most of which turned out to have natural causes or earthly interference. The famous WOW signal, detected in 1977, remains one of the few mysteries. It was a strong, clear signal lasting just 72 seconds, coming from the direction of the constellation Sagittarius. It never repeated, and no one knows where it came from. The silence doesn't necessarily mean no one's out there. The universe is unimaginably vast, and our search has barely begun. It's like dipping a glass into the ocean and concluding there are no fish because the glass came up empty. Some scientists have suggested expanding SETI beyond radio, to optical or infrared signals, or even to the detection of technosignatures. Indirect evidence of technology. That might include unusual chemical compositions in a planet's atmosphere, waste heat from large-scale energy use, or structures that partially block a star's light, such as a hypothetical Dyson sphere, a vast collection of satellites built to capture stellar energy. We haven't found anything like that yet, but the search continues. It's one of the few scientific pursuits that forces us to balance precision with humility. In the meantime, astrobiologists study extreme environments on Earth to learn what might be possible elsewhere. We've found microbes living in boiling acid, bacteria surviving inside nuclear reactors, and organisms frozen in Antarctic ice that can revive after decades. These discoveries show that life is astonishingly resilient. If it can survive here under conditions that mimic Mars or Europa, then it could certainly survive out there. One of the more curious lessons of modern science is that the limits of life are far broader than we ever imagined. A century ago, scientists thought all life required sunlight and oxygen. Today we know of organisms that live without either, feeding on sulfur, iron, or hydrogen gas. The planet itself is full of life forms that quietly contradict our assumptions. That's why every time we search another world, we carry that same quiet hope. Maybe somewhere beneath ice or rock, there's something alive, waiting to be seen. The search for life, whether microbial or intelligent, is ultimately a reflection of us. It's not just about discovering something out there. It's about asking what kind of universe we live in. Is it a lonely one, where life happened only once? Or a crowded one, where the silence is simply the sound of distance? The data so far tell us only this: the universe is full of potential. But potential doesn't mean presence. And that tension between what could be and what is leads us straight into one of science's greatest puzzles. If life can arise so easily, and if there are so many worlds that could host it, then where is everybody? In the summer of 1950, at Los Alamos National Laboratory, a group of scientists were walking to lunch. Among them was the physicist Enrico Fermi, one of the greatest minds of his time. The story goes that as they discussed the growing number of UFO sightings in popular culture, Fermi suddenly asked a simple question that would echo through science for decades. Where is everybody? It was a straightforward question with enormous implications. By Fermi's own calculations, there are billions of stars in our galaxy, many older than the sun. Even if a small fraction of those stars had planets, and an even smaller fraction of those planets developed intelligent life, there should still be thousands, perhaps millions, of advanced civilizations in the Milky Way. If that's the case, then statistically speaking, someone should be out there. We should have heard from them by now. And yet, the universe remains silent. That contradiction between the high probability of extraterrestrial life and the absence of any evidence is what we now call the Fermi paradox. To understand how strange this silence really is, let's take a quick tour of the numbers. There are roughly 400 billion stars in our galaxy. If even 1 in 5 has a planet in the habitable zone, that's about 80 billion potentially life-friendly worlds. If just 1 in 1,000 of those develops intelligent life, that still leaves 80 million civilizations. So why haven't we seen or heard from any of them? Over the years, scientists and philosophers have proposed dozens of possible explanations. Some comforting, some unsettling, and all worth considering. One possibility is distance. The universe is vast, unimaginably so. The nearest star system, Alpha Centauri, is about 4.3 light-years away, which means even a radio signal would take over 4 years to reach us, and another 4 to get a reply. Most of the stars in our galaxy are far farther away, so maybe the signals are out there, but they're simply too faint or too far for us to detect. Another possibility is timing. Civilizations might rise and fall over cosmic timescales. Maybe life is common, but technological civilizations are short-lived. A species could destroy itself through war, resource depletion, or climate collapse long before developing interstellar communication. If so, perhaps others have come and gone, leaving only their ruins or faint radio echoes drifting through the void. Some scientists call this the Great Filter. The idea that somewhere between the emergence of life and the rise of advanced technology lies a step so difficult that almost no one passes it. The Great Filter could be behind us, meaning Earth got lucky, or it could be ahead of us, meaning our biggest test is still to come. Then there's the zoo hypothesis, the suggestion that advanced civilizations know we're here, but have chosen not to contact us, perhaps to let us develop naturally. In that scenario, Earth is like an exhibit in a cosmic wildlife preserve. Interesting to observe, but not to interfere with. It's a playful idea, but it raises serious questions about how we'd even recognize a civilization far older and more advanced than ours. Their technology might be so different that we wouldn't know what to look for. To an ant, a skyscraper doesn't look like technology. It's just part of the landscape. We might be the ants in someone else's city. There's also the possibility that communication is simply too difficult. Our methods, radio waves, lasers, might be primitive by cosmic standards. Maybe advanced species use forms of communication we can't yet imagine, like neutrino signals or quantum entanglement. Or perhaps they communicate in ways that aren't even physical, networks of consciousness that exist beyond space and time. A more unsettling possibility is that the galaxy isn't full of civilizations at all. It's full of tombs. Maybe life arises often, but intelligence tends to destroy itself. The same drive that leads to technology also leads to weapons, environmental collapse, or artificial intelligence that outpaces its creators. If that's true, then the silence of the stars might not be emptiness. It might be a warning. But there's a gentler interpretation too. Maybe we haven't heard anything because we haven't been listening for long enough. Humanity has been using radio technology for barely a century, a cosmic blink. If intelligent life has existed elsewhere for billions of years, our window of observation is vanishingly small. We could easily miss each other in time. There's also the issue of expectation bias, the human tendency to imagine aliens as roughly similar to ourselves. We expect them to build machines, send signals, and think logically. But what if intelligence doesn't always follow the same path? What if, on another world, life evolved to be cooperative instead of competitive? Or biological intelligence merged seamlessly with its environment, producing no detectable technology at all? A planet covered in self-aware forests or hive-like microorganisms might never call us, even if it were conscious. Some researchers, including the late Carl Sagan, suggested that even if we never find evidence of others, the act of searching is deeply meaningful. Because when we look for life elsewhere, we're really learning about our own. We're forced to confront the fragility of civilization and the narrowness of our perspective. The Fermi paradox is, in a sense, a mirror. It shows us how young, how noisy, and how impatient we are as a species. We expect an answer, a message, a signal, in decades, while the universe measures time in eons. Perhaps the silence isn't a mystery at all. Perhaps it's just the sound of a cosmos that's still waiting for us to listen properly. And maybe, someday, when our technology grows more refined or our patience deeper, we'll finally pick up a signal, a faint whisper across light years, proof that we're not alone. Until then, the paradox remains, a question that hangs over us like the night sky itself. If life can exist elsewhere, why hasn't it said hello? When we talk about life, we usually mean life as we know it, carbon-based organisms that depend on water and oxygen, and that live within a narrow temperature range. But that's only one recipe. It's the version that worked here on Earth. The universe may use other recipes entirely. Astrobiologists call this idea alternative biochemistry. The possibility that life could be built on different chemical foundations using elements and solvents unfamiliar to us. It's a serious scientific hypothesis, not just science fiction. To understand why, let's start with a simple observation. Life is, fundamentally, chemistry that sustains itself. It's a system that captures energy, uses it to maintain organization, and makes copies of itself. There's nothing in that definition that requires water or even carbon. Those are just the ingredients we happen to know. Take silicon, for example. It sits just below carbon on the periodic table, and like carbon, it can form 4 chemical bonds. That means it too can build complex molecules. Some scientists have wondered whether life could exist on a silicon basis instead of carbon. Silicon has appeared in science fiction for decades. Think of crystalline life forms or rock creatures. But real chemistry does pose challenges. Silicon bonds are generally less flexible than carbons, and silicon-based molecules tend to be solid at the temperatures where carbon compounds are liquid. Still, under different conditions, say on a hotter planet or in a solvent other than water, silicon chemistry might flourish. There's also ammonia, a liquid that behaves somewhat like water but at much lower temperatures. On extremely cold worlds, where water would freeze solid, ammonia could stay liquid, providing a potential medium for life. Some scientists suggest that certain moons or exoplanets might host ammonia-based ecosystems, slow, cold, and entirely alien, but still alive in a meaningful sense. Then there are hydrocarbon solvents, like methane and ethane, which we already see on Titan. These substances could support exotic chemistry at frigid temperatures. Reactions would happen millions of times more slowly than in water. But over geological timescales, even slow chemistry can lead to complexity. When NASA and other agencies design missions to search for life, they increasingly think in these broader terms. Instead of asking, "Is there water?" they now ask, "Is there a solvent that allows chemistry to happen? Is there a source of energy? Are there molecules that can store information or catalyze reactions?" It's a shift from looking for Earth-like life to looking for life-like systems. One of the most fascinating developments in this field came from synthetic biology on Earth. In 2010, researchers at the J. Craig Venter Institute created a cell with a completely synthetic genome. DNA built from scratch using 4 standard nucleotides. 5 years later, another team went further, adding 2 new letters to the genetic alphabet. Those artificial bases could be copied and expressed by living cells, expanding the fundamental code of life. That experiment proved something remarkable. Life's chemistry is not fixed. You can rewrite it, expand it, even alter its alphabet, and it still works. If we can do that here, in a laboratory on Earth, what might nature have done elsewhere, over billions of years? Astrobiologists like Sarah Seeger and Lynn Rothschild have argued that we must remain open to radically different life forms. Some might not even use DNA or RNA. They could store information in polymers we've never seen, or rely on metallic structures instead of organic ones. One possible clue lies in the strange behavior of extremophiles, organisms on Earth that thrive in what we once thought were deadly conditions. There are bacteria that survive in boiling acid, others that live miles underground, feeding on pure rock, and tiny tardigrades that can endure the vacuum of space. These examples remind us that life constantly defies expectation. If we didn't already know about them, we might have dismissed their existence as impossible. So when we imagine alien life, we must be humble. Our senses and imaginations are shaped by one planet, one chemistry, one experience. But nature, as far as we know, has no obligation to repeat itself. It's entirely plausible that life elsewhere doesn't look like life at all. It might not have cells, or metabolism, or anything resembling what we'd recognize. It could be electrical, a network of charged particles living in the atmosphere of a gas giant, feeding on lightning, or magnetic, based on patterns of energy in plasma clouds. To us, that might look like random noise. To them, it might be thought. These are speculative ideas, of course, but they highlight an important truth. Our definition of life is limited by our perspective. Every scientific discovery about biology on Earth, from microbes in nuclear reactors to worms in Antarctic ice, expands that definition a little more. That's why some scientists prefer to focus not on the word life, but on the concept of complexity, systems that use energy to maintain structure and adapt. By that measure, even non-biological processes, like self-organizing crystals or chemical networks, could represent early steps toward something we might one day call alive. Ultimately, what all of this shows is that life is not a single event. It's a spectrum of possibilities. Water-based, methane-based, carbon-based, or something yet unimagined. The universe may be experimenting in 1,000 ways, quietly, all at once. And the more we learn about those possibilities, the more we realize that Earth is not the rule. It's just one example. When we look up at the stars, we might be seeing not just other worlds, but other kinds of chemistry, other ways of being, other definitions of existence itself. And that idea, that life might come in forms we can barely comprehend, leads us to a deeper question. If the universe is so generous with its chemistry, why does it seem so quiet? We've seen that the conditions for life are everywhere. But what about intelligence? What about civilizations like ours, capable of curiosity, science, and wonder? Perhaps the silence doesn't mean emptiness. Perhaps it means that most life stays simple, content to remain microbial, safe from the dangers that come with awareness. Or maybe, just maybe, there are civilizations out there that grew wise enough to stop shouting into the void and simply chose to listen. When scientists look out into the universe, one fact stands out above all others. The ingredients for life are everywhere. The same atoms that make up our bodies, carbon, oxygen, nitrogen, hydrogen, are not rare or exotic. They're some of the most common elements in existence. If you take a handful of interstellar dust or a sample from a distant comet, the chemistry will look familiar. The universe doesn't just tolerate life's building blocks, it mass produces them. But how did that happen? To understand why the cosmos seems so friendly to life, we have to go back to the beginning, to the birth of the elements themselves. In the first few minutes after the Big Bang, the universe was unimaginably hot and dense. Only the simplest elements could form, mostly hydrogen and helium, with a trace of lithium. There were no heavy elements yet, no carbon, oxygen, or iron. The early universe was chemically simple, almost sterile. Then came the stars. Stars are the forges of creation. Deep within their cores, gravity squeezes hydrogen atoms together until they fuse into helium, releasing energy in the process. The light and heat we see as starlight. As stars age, they continue that process, fusing helium into heavier and heavier elements. Carbon, oxygen, nitrogen, silicon, and eventually iron. But the real magic happens when massive stars die. When such a star exhausts its fuel, its core collapses and then explodes in a supernova. One of the most powerful events in the universe. In that violent moment, the extreme heat and pressure create even heavier elements, like gold, silver, iodine, and uranium. Those materials are then thrown into space, where they mix with gas and dust and eventually form new stars, planets, and, in at least one case, people. Every carbon atom in your body was forged in a dying star. Every molecule of calcium in your bones, every atom of iron in your blood. All of it was once part of a supernova. The poet's line, "We are made of star stuff," is not just metaphor. It's literal physics. This stellar recycling process, called nucleosynthesis, means the universe enriches itself over time. The first generation of stars made the ingredients for planets. The second and third generations, formed from that enriched material, made the ingredients for life. In other words, the longer the universe exists, the more fertile it becomes. We now know that water, too, is remarkably common. Astronomers have found water vapor in the atmospheres of distant planets, in the tails of comets, and even in interstellar clouds between the stars. Some of those clouds contain enough water to fill Earth's oceans many times over. Comets, in fact, may have been the couriers that brought water and organic molecules to the early Earth. In their icy hearts, they preserve chemistry from the dawn of the solar system. When they strike young planets, they deliver that chemistry like seeds in the soil. This process of worlds being seeded by cosmic material could happen everywhere. Meteorites traveling between planets might carry organic compounds from one system to another. Over billions of years, the galaxy could be quietly cross-pollinating itself with the ingredients for life. Even the physical laws of the universe seem curiously well suited for complexity. The strength of gravity, the charge of the electron, the energy of nuclear reactions, all these constants fall within narrow ranges that allow stars, planets, and chemistry to exist. If they were even slightly different, the universe might have collapsed, expanded too quickly, or produced only hydrogen and helium, no carbon, no oxygen, no life. This has led some scientists and philosophers to talk about the anthropic principle, the idea that the universe appears fine-tuned for life because, well, we're here to notice it. If the laws of physics were not conducive to life, we simply wouldn't be around to ask why. Others suggest that maybe there are many universes, a vast multiverse, each with different physical laws. We just happen to live in the one where life is possible. Regardless of which explanation is true, the result is the same. Our universe makes life not only possible, but likely. From the smallest scales of quantum physics to the largest structures of galaxies, there's a kind of harmony, a chain of events that leads step by step from chaos to order, from gas to stars, from stars to planets, and from planets to living beings capable of asking how it all began. This doesn't mean life is common, only that the universe is generous with its ingredients. But generosity matters. It means that the spark that started here could just as easily have ignited elsewhere. If the laws of nature are the same everywhere, and all evidence says they are, then what happened on Earth is not a miracle. It's a pattern. In the end, it's hard not to feel a sense of connection. The hydrogen in your body came from the Big Bang. The carbon and oxygen came from ancient stars. The water in your veins was once ice drifting through space. You are, in the most literal sense, a child of the cosmos. When we search for life beyond Earth, we are not just looking for something foreign. We are looking for family, for other branches of the same cosmic tree. And maybe that's why the search feels so deeply human. It's not just science. It's longing. The universe made us from its own material. And now, through curiosity, it's using us to look back at itself. But for all its generosity, the universe still holds one enduring mystery. If life can emerge so easily, and the elements for it are everywhere, why is Earth the only place we've confirmed it so far? Perhaps that's not the right question to ask. Perhaps the real mystery is not whether life exists elsewhere, but why we exist at all, here, in this brief moment of cosmic time. And while scientists continue to search the skies, they also turn their gaze inward, to our own fragile world, to understand what makes life here so resilient and so rare. Every search tells us something about the seeker. When we look for life beyond Earth, we're not just studying planets and chemistry. We're studying ourselves. The question, are we alone, is not only scientific, it's existential. It touches on identity, purpose, and belonging. For centuries, people have looked to the heavens for meaning. The stars have been gods, guides, calendars, and companions. Now, with satellites and spectrometers instead of myths, we're still looking. But the longing is the same. In many ways, the search for alien life is a mirror. It reflects our hopes and our fears. When we imagine a universe full of civilizations, we picture connection, that we're part of something larger, that consciousness didn't stop with us. But when we imagine a silent cosmos, we see fragility, that maybe life is rare, and that our tiny blue world carries something irreplaceable. Both possibilities are profound. If we're not alone, it means the universe tends toward life, that evolution and intelligence are woven into its fabric. If we are alone, then life here is even more extraordinary. A single, improbable bloom in a vast, indifferent sea. Either way, the lesson is the same. Life is precious. Astronauts who have seen Earth from orbit often describe a strange emotional experience, something psychologists call the overview effect. From space, the borders vanish. The wars and divisions of humankind shrink into invisibility. What they see is a fragile, glowing sphere, wrapped in a thin film of air, floating in darkness. That image changes them. It reminds them that everything we love, every language, every culture, every memory, exists on that pale blue dot. And it's the only place we know where life thrives. Carl Sagan once said, "To preserve our planet, we must see it as it truly is, a small stage in a vast cosmic arena." That's not a reason for despair, it's a call for perspective. Because understanding how rare and interconnected life is gives it meaning. The search for life beyond Earth sharpens that awareness. Each probe we send, each telescope we launch, each signal we listen for, they all remind us of what's at stake here at home. When scientists study Mars or Europa, they're also studying Earth's own past. The moments when chemistry first became biology. When we analyze exoplanets, we're asking, what makes a world habitable? And by extension, what keeps our own world habitable? In that sense, astrobiology isn't just about aliens. It's about climate, sustainability, and time. It's about learning how planets live and how they die. We've learned that life depends on a delicate balance of factors: temperature, atmosphere, radiation, chemistry, magnetism. Earth maintains that balance beautifully, but not automatically. It's held together by feedback loops, ecosystems, oceans, clouds, and by choices we make. If we ever do find life elsewhere, especially intelligent life, the first message it would send us, even before we could translate it, would be this: life can survive if it respects its home. Every living planet, no matter how different, must learn the same lesson to live within its limits. That idea connects science with ethics. The discovery of alien life wouldn't just be biological news, it would be philosophical news. It would force us to redefine words like unique, important, and alive. It would challenge religions, rewrite textbooks, and perhaps humble us in the best possible way. Because right now, humanity stands at an unusual crossroads. For the first time in history, we have the power to explore other worlds, and the power to destroy our own. We can send robots to Mars, but we also change Earth's climate. We dream of finding life elsewhere, even as we erase habitats here. In that contrast lies a quiet truth. The more we look for life out there, the more we realize how vital it is to protect life here. This realization is part of a long evolution in human thought. There was a time when people believed Earth was the center of the universe. Then we learned we orbit the sun. Then that the sun is just one star among billions in the Milky Way. Then that our galaxy is one among trillions. With each step, the universe grew larger, but our sense of wonder grew with it. And now, the next step in that evolution might not be about where we are, but who we are. Living beings made of ancient atoms, briefly conscious of themselves, looking out across time and space for kin. Even if we never find anyone else, that journey changes us. It teaches patience, humility, and gratitude. It reminds us that life doesn't need to be universal to be sacred. Perhaps one day we'll confirm another biosphere. A world where microbes swim in alien seas, or where minds think under a foreign sun. And when we do, we'll finally have proof of something many people already sense: that life is not an accident, but a tendency. That the universe, when given time, naturally awakens to itself. But even if that day never comes, the act of searching still gives meaning to our own existence. It's what humans do best. We ask questions, we reach, we imagine. The cosmos may be silent, but the silence itself is an invitation to listen more carefully, to look more deeply, and to cherish the rare, improbable gift of being alive. And as we look outward, we inevitably turn inward. The stars remind us that our home, small, blue, and fragile, is worth protecting, not because it's the only one, but because it's ours. And maybe, just maybe, out there among those distant points of light, there's another world looking back, wondering the same thing. If you've made it this far, through stars and dust and silence, you've journeyed farther than most people ever do. Not through space, but through thought. The search for life beyond Earth begins with telescopes and spacecraft, but it ends, always, in the human mind. Because every question we ask about the universe is really a question about ourselves. Why are we here? Are we special? Are we part of something larger? Science gives us data. Wonder gives us meaning. And somewhere between those two lies the truth that life, in any form, is the universe becoming aware of itself. When we stare at the night sky, we're not just looking outward. We're looking backward in time. The light from distant stars began its journey millions of years ago. Before humans existed, before Earth even looked like Earth. And yet that light finds its way to our eyes, crosses the emptiness, and lands gently on our retinas. Think about that for a moment. The atoms in your body were born inside stars, scattered across space, drawn together by gravity, assembled into a planet, and eventually into you. A being capable of looking back at the stars that made you. That's not magic. It's physics. But it feels like magic anyway. Every part of you is ancient. Yet here you are, living in a moment so brief that the universe barely notices. And still, you notice it. The great irony of existence is that the cosmos is almost entirely empty. And yet it created beings who cannot stand emptiness. We fill it with stories, curiosity, and love. We send probes and poems into the dark just to say, we were here. We wondered. Maybe that's all the proof the universe needs, not a signal, not a civilization, but the quiet persistence of beings who look up and care. If we ever do find life elsewhere, it will not diminish our own. It will expand it. It will show that life is not confined to a single world, but is a property of the cosmos itself, as natural as gravity, as inevitable as starlight. And if we never find it, then this tiny oasis we call Earth will be even more precious. A rare miracle in an ocean of silence, where atoms once belonging to stars have learned to feel joy and sorrow and awe. Perhaps one day, long after we're gone, some distant civilization will look up at its own night sky and notice a faint signal, a trace of our existence, drifting through the void. And maybe they'll wonder, as we do now, whether they're alone. In that moment, across unimaginable distance and time, two forms of life, separated by light years, will share the same simple thought. We are part of something vast, and that is enough. So as you lie there listening to the hum of your own small corner of the cosmos, remember, you are made of starlight. You are the universe, briefly awake, quietly dreaming of itself. And in that dream, there is beauty. There is meaning. There is connection. The stars will keep shining. The planets will keep turning, and life, wherever it exists, will keep wondering. Good night.